Hello, everyone, and welcome to Algebra 2, Section 3.2, Complex Numbers. So complex numbers are at the top of the chain, so to speak, when we talk about all the different kinds of numbers there are. I'm actually going to work my way up from the bottom to show you what all the different number types are, because that's how you learn them. So when you are small, you naturally start counting at 1. The natural numbers are the set of 1, 2, 3, 4. So it's very easy to remember what the natural numbers are because that's how you naturally learn to count. And then you get a little older and you find out about 0. I remember this whole numbers has the 0 in it, and literally that is the only difference. 0, 1, 2, 3, 4. ... just means it continues in that pattern. Integers are whole numbers and their opposites. So I'm going to put my ... on the other side as well now. So going all the way from negative infinity, -5, -4, -3, -2, -1, 0, 1, 2, 3, ... So integers are just whole numbers and their opposites. Now we get into rational numbers. Rational numbers is anything that can be written as a ratio. Anything that can be written as a ratio. That's the definition of a rational number. So even a number like 3 is a rational number because you could write it as 3 over 1. 0.75 is a rational number because you could write it as 3/4. Even a number that's repeating, like 0.4, repeating, which means that little bar means 0.444444. Even that can be rewritten as 4/9. Any number can be, almost any number can be written as a ratio. So your whole life, pretty much, you've dealt with mostly rational numbers. And a subset of that are the integers, which are just the numbers that are over 1, not 3/4. And then the whole numbers is a subset of integers. That's why they keep going down like that. These are subsets. So what would be an example of an irrational number? An irrational number is a number that does not have a pattern. And so it's going to have 2 parts. And it goes on infinitely. So some examples of that would be things like square root of 2. If you type that into your calculator, it'll give you a decimal, but just the first 9 places. It would keep going and going and going. And unlike 0.4 over here that also keeps going forever, at least this one has a pattern. This one goes on infinitely and does not have a pattern. So I always remember these as somebody who is being irrational. Not only do they just keep going on and on and on, but they don't have a pattern. They're not making any sense. They're being completely irrational. So pretty much there's 2 things that you have to look for irrational numbers. One is any kind of square root that cannot be simplified. So the square root of 4, not on my list, because that could be made into 2. And then the other thing that's irrational is pi. Pi is approximately 22 over 7, but it's not 22 over 7. Pi is a very valuable ratio that doesn't have an exact answer. It's just 3.14, blah, blah, blah. It keeps going on. So if you take all the rational numbers, things that can be written as a ratio, and you take all the irrational numbers and you put them together, we gave them the name real numbers. And that's what you've pretty much been dealing with your whole life. You've seen the square root of 2, so you've done real numbers. So what would be counter to that? Imaginary numbers. And imaginary numbers, and notice this is the only one that actually had a note because I'm assuming that everything else is review. But imaginary numbers is what we're going to do today. And the imaginary number is just a man-made invention where somebody said, instead of calling something I or square root of -1, we're going to call it I. So if you have the square root of -4, you can do the square root of 4, that's 2. But what about the negative? That's like still stuck underneath the radical. And that's kind of an annoying notation. So literally, somebody just made this up, and the whole world agreed that if you ever see this, the square root of -1, you can change that to I. And of course, you don't need to show this step. You can just immediately say, well, the square root of 4 is 2, and the negative becomes an I. And then our name for imaginary combined with real would be a complex number, A plus BI, meaning it's complex. You might have part of it that is real and part of it that's imaginary, something like 3 plus 2i. Try and think about that. You guys have seen when you've done the quadratic formula, 3 plus or minus the square root of 5. So now, if instead you have 3 plus or minus the square root of -5, you're going to end up writing that as 3 plus or minus I square roots of 5, because that negative is going to be, under the radical, is going to be rewritten as an I. So this part would be real, and this part would be imaginary. And so together, they make something called a complex number. All right. So for the following, it says determine which subsets of the set of complex numbers contain each number. There could be more than one answer for them. So take a minute, pause the computer, and see how many of these you can get on your own. Or just don't look while I write them all down. Okay, so maybe you were checking your work as you went, but I'll explain them really fast. So the square root of 9 is 3, and if you start at the top, 3 is real, and it's rational, and it's an integer, and it's whole, and it's natural. The square root of 0 is 0, which is real, rational, it's an integer, it's a whole number, but it stops at natural. It is not on my natural list. C is -2, which is real. Okay, it would only have a negative under the radical for it to be imaginary. So it's real, it's rational, it's an integer, but it's not a whole number. Integers are the negatives. Square root of 4/9 is equal to 2/3, which is real and rational, but it's not an integer, a whole number, or a natural number because it's a fraction, so it stopped at being a rational number. Square root of 2 is the example I gave you for a number that was real but irrational, and by definition, the square root of -1 is I, which is imaginary. So a thinking question for you is it possible for a number to be both whole and natural? Natural and rational. Again, it would be great if you paused this and tried to think of an example for each. So for whole and natural, I'm going to use 4. It's a whole number because it's 1, 2, 3, 4, and it's natural It's both of them. Natural and rational. We can use 7. That's definitely a natural number, a counting number that a child would use. And it's rational because it can be written as 7 over 1. Rational and irrational. No. It is either one or the other. It cannot be rational and irrational at the same time. Real and imaginary. No, there is no example. I guess I should put, for example, here in your notes so that you realize that those aren't the only answers. Those are just 2 possibilities. Yeah, something is either real or imaginary. Okay, so the square root of a negative number. So when I see a square root, I normally would just say the square root of 25 is 5. But since there's a negative under the radical, you're going to write it as 5i. You could write it as 5 times the square root of negative 1. But like I said, somebody has invented something to replace this, and that is the I. So in general, my best advice for you is if you have a number, I want you to break it down into 2 parts. Parts you can do, meaning parts you can simplify, and parts you can't. Probably did this in Algebra 1, but maybe you don't remember. And the key to being able to break it down into parts you can do and parts you can't is to know your list of perfect squares. You're probably going to run and write this down somewhere where you can get to it handy. All I'm doing is squaring every whole number, now that you know what those are. 6 squared, 7 squared, 8 squared, 9 squared. And of course I could keep going forever, but I'll stop there. So when I see a 72, luckily, unlike factoring, you don't have to think, what are all the factors of 72? You only care if 1, 4, 9, 16, 25, 36, 49, I'm already too high, is a factor of 72. So the negative is always going to go in the part you can do, because you are going to fix that and make it an I. So 36 times 2. 36 is on our list, 2 is not. So I've broken it down into a part I can do. Oops. And the square root of 36 is 6. The square root of the negative is I. And this stays under the radical because it cannot be simplified. This is multiplied. When you see negative 5 square roots of negative 9, that's how we pronounce that. These 2 things are attached by multiplication. You don't have to write that. I'm just trying to show you. So negative 5 times, and the square root of 9 is on our list, so I don't need to break it down into parts I can do and parts I can't. It's just 3i. And you can multiply those. Negative 15i. The next one is just 2i. So if it's on the list, if it's a perfect square, you can just simplify it. If it's not on the list, the negative is in the part you can do, and you have to break it down. So what factors of 12? See, there's only 3 to check. At 16, you're already above 12. And 1 is actually kind of useless because obviously 1's always a factor. So does 4 or 9 go into 12? Of course, 4 and 3. So I've broken 12 down into part I can do and part I can't. The square root of negative 4 we just decided becomes 2i, and the square root of 3 has to stay underneath the radical. Now this negative and this negative, they do not combine. The one under the radical becomes 6i. So this final answer is negative 6i. Be careful not to say a negative times a negative makes a positive, as tempting as it is. So again, I have a big number that I'm not that familiar with, but fortunately, I only have to try numbers that are on the list. So does 4 go into 54? No. Does 9 go into 54? Yes. So 2 times the square root of the negative is in the part I can do, and 9 goes into 54. times 6. So then I get 2 times 3i times the square root of 6. And the parentheses aren't really necessary for that. I put them here because I didn't want you to think it was 23, because it's actually going to be 6i square roots of 6. That's how you take the square root of a negative number. So now we can add, subtract, multiply i's. These are great. They are just like x. Okay? So if this had been 8 minus x plus 5 plus 4x, that's literally all you're going to do. So I get to combine numbers with numbers, or real with real, and imaginary with imaginary. Now be careful. You are welcome to distribute in your head. You are smart and capable, but I'm going to tell you right now, if you go straight to the answer and you forget to distribute to every single term, I'm not giving you partial credit, because this is the one time I highly recommend, I've seen it for too many years, distributing the negative, especially when the second one is negative. In your head, it just accounts for it somehow. So it's easy to make that mistake. But this step allows me to give you partial credit if you just add wrong. And you get 4. You don't have to write 0i. Just like an x, it just goes away. Again, I personally would take the 10 seconds to rewrite this step so that you can then get it correct after that. So numbers with numbers and i's with i's. So adding and subtracting is super easy. To multiply, it's also super easy. This is going to be negative 30i squared. But the reason this gets its own section is you may never leave an I squared in the problem. I squared is equal to negative 1. And I'll quick show you why. Because I squared is I times I. And I, remember, is the square root of negative 1. So the square root of negative 1 times the square root of negative 1 is the square root of negative 1 squared. And when you square a square root, they're inverse operations. They undo each other. So you're just left with negative 1. If you're like, what? That's okay. Just memorize this. I squared is negative 1. So as your final step, the I squared becomes negative 1. And the final answer is 30. You can distribute just like you would an x. So this becomes negative 24i plus 4i squared. But remember, you can never leave an I squared in the problem. So this is going to become negative 24 plus 4 times negative 1. Oops, there's an I there. Which is negative 24i minus 4. So most algebra books, math books in general, like to put complex numbers in the form a plus bi. So you're going to see them rewrite it as negative 4 minus 24i. That is not necessary for me. It's commutative, which means 3 plus 2 is the same as 2 plus 3. I do like it when polynomials are in descending order. That's nice. You know, x squared, x, that's easier to read. But I think with i's, you really don't need to do that. But I want you to know that your book will always express the answer as a plus bi. And that's considered standard form. All right, you might want to try the next 2 on your own, the next 3 actually. So I'm going to quick write the answers here in the margin before I do them in case you want to venture out. You can write them down also. Number 5, which you can't quite see, is going to be 8i plus 1. Hopefully you're doing them on your own, but I will do them now. So this first one, I'm going to FOIL, first, outer, inner, and last. There used to only be one thing that you had to do next, which was to add these together, but now you also have to change this to a -1. So there's two things to do now in FOIL. -36 plus 71i plus 14. And now you can combine these two for a final answer of -22 plus 71i. Next one. First, outer, inner, last. That gives me 15. These two make 2i. And this is minus a -1, which gives me +1 for a final answer of 16 plus 2i. Last one in this section. It's not FOIL, it's just distribute, which would give me 8i minus I squared, which is 8i minus a -1. I squared is -1, which is 8i plus 1. So now we've learned how to add, subtract, and multiply I. Now we're going to do some quadratic equations. So this is review. You have everything in here you've already done. The only difference is that the i's will be in the answers instead of just real numbers. So normally when I see an x squared, I set it equal to 0 and factor. So if you have an x squared, your top choice should be to set it equal to 0 and factor. Unless there's one exception, there's no x term. If there's no x term, then you can just isolate the x squared and square root both sides. And that's what I'm going to do for this one. So this is the exception right away. I isolate the x squared by subtracting 4 from both sides, and then I take the square root of both sides. So this is something that you have already been doing this year. The only difference is that now, by the way, don't forget your plus or minus when you take the square root of both sides. But now you're going to have an I in your answer. Okay? Square rooting always produces a plus or a minus. So I want to just tell you something really quick. If you are the one that square roots both sides, you need to remember the plus or minus. But if somebody just says to you, what is the square root of 4? The square root of 4 is just 2. Somebody's already put the square root in, and somebody's already decided that it's plus. It's only when you put in the square root that you have to account for both the plus or the minus. All right, I see an x squared, and I don't see an x term, so I can do this again. 2x squared is equal to -36 by adding 11 to both sides. I divide both sides by 2, and then I take the square root of both sides. Don't forget that that's always going to produce a plus or a minus. I break my 18 into parts I can do. The negative is always with the can do. I quick think of my list. 1, 4, 9, 16. I'm already at 16. 16 is not going to be a factor of 18. So it's either 4 or 9, which of course it's 9. And so it's plus or minus 3i square roots of 2. What does it mean to find the zeros? Finding the zeros is finding the x-intercepts. And what's special about an x-intercept is that an x-intercept is where the graph crosses the x-axis. And in every one of these cases, the y-coordinate is 0. The y is 0. The f of x is 0. So to find the zeros, you're going to make the f of x 0. I see an x squared in my equation, but no x term. So I can just subtract 20, divide by 4, and take the square root of both sides. Don't forget your plus or minus. So when you break this down into parts you can do and parts you can't, the only thing you can do is the negative. So the final answer is just plus or minus I square roots of 5. Last one. Find the zeros. So 0 is equal to 9x squared plus 1. Negative 1 is 9x squared. Negative 1/9 is x squared. I take the square root of both sides. I don't forget my plus or my minus. So 1/9 is a perfect square. 1/3 times 1/3 makes 1/9. That's what it means to be a perfect square, that a number times itself equals something. That makes that something a perfect square. So this is 1/3 I. So you can write that as plus or minus 1/3 I, but if you do that, make sure the I is right, like centered. If you are sloppy because you're writing on a piece of paper, sometimes kids will be on a piece of paper, and so they'll write x is equal to plus or minus, and they have to put the 1 up here, 1/3, and then they write the I. You see how that looks like the I is on the denominator? I will take off for that. That is not correct. Sometimes people are like, oh, I'll slant it then. 1/3I. That's worse. That definitely looks like it's on the bottom. Don't do that. If you really wanted to fix it, when you're multiplying a fraction by a whole thing, I was going to say a whole number, but I is not a whole number, you can put it on the top and put it over 1. Just like we were talking about making whole numbers into rational numbers. It's just over 1. So technically, if that I is anywhere, it's on the top. So you can write it like this, or you can write it as plus or minus I/3. These are the same. You can either go off to the side or in front, but make sure it does not look like it's on the bottom. So this next little section looks hard, but it's super easy, so don't be intimidated. It says find the values of x and y that satisfy the given equation. Well, you can't make a real imaginary or an imaginary real. So since this is real on this side, this is real on this side, I can kind of go off and say the 2x must be equal to the 5, or to the 10. I'm ahead of myself. And therefore, x must be 5. And the imaginary part must equal the imaginary part. So y must be a -7. That's really all they're looking for. I'll go ahead and give you the next 2 answers in case you'd like to try it yourself. Oh, I guess this one, there we go. So x is equal to 9 and y is equal to -3. X is equal to -4.5 and y is equal to 3/4. So hopefully you stop the video and try it on your own. But I'll do it for you. Real has to equal the real part, so x is equal to 9. And imaginary has to equal imaginary. So 3i is equal to -yi. So I cancel the i's. And I have 3 is equal to -y, so to how to get y by itself, divide both sides by -1. And you get y is equal to -3. The real is equal to the real, so 9 is equal to -2x. Divide both sides by 2, and you get -9/2, which is the same as -4.5. The imaginary is equal to the imaginary, so 4yi is equal to 3i. I. So in essence, 4y is equal to 3. The i's can be either divided away, or you can just think the coefficient has to be the same. Divide both sides by 4, and you get 3/4. All right, so one last little extension problem before we wrap up here. It says make a table that shows the powers of I from I to the first to I to the eighth in the first row, and the simplified forms of the powers in the second row. Describe the pattern you observe in the table. Verify the pattern continues by evaluating the next 4 powers of I. I would love for you to do this on your own. You will grow as a mathematician if you do, but obviously I'm going to do it for you. So I to the first, I squared, I third, I to the fourth, I to the fifth, I to the sixth, I to the seventh, and I to the eighth. And then our prediction is going to be with the next 4 powers, and we'll see if we can figure out the pattern. So I to the first can't be simplified. It's just I. I squared, we already learned, is -1. So for I cubed, I'm just going to draw a line. So for I cubed, I like to think of it as I times I squared. And since I squared is -1, it's I times -1, which gives me -I. I to the fourth, I like to think about as I squared times I squared. That would make I to the fourth, which would be -1 times -1, which would just be 1. For I to the fifth, I can think of I to the fifth as, notice I keep using I squared. I use it as often as I can. Actually, no, I'm going to use one better. Now that I've reached I to the fourth, I'm going to use I to the fourth times I, which would make I to the fifth, right? 4 i's and then 1 more would make I to the fifth. Why am I excited about using I to the fourth? Because I to the fourth is just 1. So 1 times I is I. I to the sixth, I'm going to use my I to the fourth again. Do you know what I have to multiply by to make 6 of them? 2 more. I to the fourth times I squared is I to the sixth, right? I to the fourth times I squared is I times I times I times I. There's 4 i's times 2 more, and we can rewrite that as I to the sixth. Why did I choose that combination? I could have done I cubed times I cubed, but I like I to the fourth because it simplifies to 1. And I squared simplifies to -1. So I to the sixth is just -1. You see the pattern yet? If you do, you can skip ahead. I to the seventh is going to be I to the fourth. I'm going to keep using that as long as I can. Times I third. I to the fourth is 1. And I to the third is -I. When I multiply them, I get -I. Last one. I to the fourth times I to the fourth is 1 times 1, which is 1. Do you see the pattern? I, -1, -I, I. I, -1, -I. So how do I expect this to end? I, -1, -I, 1. So every multiple of 4, the 8, the 12, the 16 ends up being just 1, which really helps you simplify things that are enormous. So if, for example, on the extra credit on the test, I were to write something like, what is I to the 101? You could say to yourself, well, I to the 100 is a multiple of 4. And every multiple of 4 is just a 1. So it would be 1 times I, which is just I. So I to the 101 is just I. And you can do that by saying every multiple of 4 is going to be equal to 1. So the i's are pretty cool. So as always, there is extra practice. You can either do that if you need it, but you have plenty of homework. So most people just save it for the test. If you're in class, we use it for class time work as well. But hopefully that all made sense. And and I'm just reading through your homework. We already did number 67 in class. This was number 67. Okay, so you already can see the answer, but now maybe you can do it on your own and make sure you really understand it. All right, have a great day.